class. Okay, now this is a series of slides called the History of Science. It's a PowerPoint and it's available on oh, I wanted to do one more thing before I started that. The take-home tests. Okay, you go to Files, Test Related, and if you do a date created search or listing, it'll be first one. Okay, and it's a problem similar to the one I showed you Thursday. Actually very similar to that. Yeah.
You just bring it in tomorrow?
Yeah, and you're gonna, when you turn in your test, you're gonna stick it up in the back. Okay, does everyone understand? And again, I'll have a take-home test problem with your tests. So when you receive the test, if you've already done the problem, don't do it again. Just staple it to the back. You're more than welcome to do it again. But remember, I don't like busy work. And that's a good example of busy work. Okay? All right. So that's where it's located. And, you know, it's, and you're gonna have the same list of assumptions. And I just changed it to how many liters of gasoline did the United States use in 2011? It's very similar.
It's crammed.
I mean, it's very similar. Very similar. Just chop off the M and substitute this one. But you're 90% there though, if you've done that, so. See, let me what happened to Canvas? Okay, so history of science. If you go to Unit 2, Files, and history, spell it right. Okay, well, I'm going to put it in Unit 2. You. Okay, I will put that up. I gotta find it on my hard drive. Okay, so let's jump back in over here. Okay, so it all started back probably before the Greeks but the Greeks were good at documenting what they've done and said. There's a lot of cultures, for example, in Africa, the Nubian, for example, that existed way before the Greeks. And they did some really cool stuff. They just not recognized. And Africa is kind of an interesting group of countries right now because they're really blooming. You know, everyone thinks that Africa is such a poor continent, but it's not. It's got tons of natural resources, and the colonialism is pretty much gone with Africa that were stealing all their resources. So anyway, we're going to start with the Greeks, but just remember that they were before that also. Okay, so two main people that come to light when we talk about physics and chemistry, and that's a guy named Democritus and a guy named Aristotle. You probably all have heard of Aristotle. Aristotle believed that everything is composed of earth, air, fire, water, not the band. Okay, earth, wind, and fire. That's what I keep, Democritus, though, had an interesting idea. He said, if I have an apple and I cut it in half, is it still an apple? Yeah, still an apple, right? What if I cut it in half again? Still an apple? Okay, what if I took out my sharp Ginsu knives and kept chopping away, chopping away? I get to the point where it's no longer an apple. Democritus said he called it no cut. In other words, no more cutting it and it remaining an apple. And he called it atomos. And that's where the word atom comes from. However, Aristotle was much more popular and probably powerful than Democritus. So up until like 1700s, Aristotle ruled in terms of what is matter. And matter is a big deal. Like, how is this pencil and this stapler? What's common about them? What's different about them? People have been contemplating this concept for many, many years. Okay, so keep the idea of two philosophers. Now, as we progress through the centuries, went through the Dark Ages, and as we start coming out of the Dark Ages into the Renaissance, some individuals known as alchemists started to arise. And they were early philosophers slash chemists slash physicists slash astronomers, mostly chemists though. And they were trying to find the elixir of life. They called it the ether. However, their employment, if you can call it that, was under the power of the king. And the king could give a rip. The king wanted more gold. So most of the alchemist's time was spent converting lead to gold. Now we do that, we can do that all the time now. It's very expensive, even though gold is $3,400 an ounce. It's still cheaper to mine the gold rather than to make it. Well, we can make it. It's called transmutation. We're converting one element to another, and that's called nuclear chemistry. However, at the time, they didn't have anything fancy like a cyclotron or just these horrendously expensive machines, basically, that physicists use. Okay, so the alchemists were part of Western Europe. They had two issues. Alchemists were very powerful in the kingdom, and they wanted to stay powerful. So one of the ways to stay powerful is to do things but not tell anyone how you did it. Now, in the modern scientific world, if you do that, you will be ousted out of your job. If you say something, you've got to prove it. Not only prove it, but you've got to be able to reproduce it, replicate what you've done, which the alchemists didn't do because that would mean sharing of their very secret information. And the way that information goes, so goes the power. The other problem is, ¿cómo se dice water en español? Agua, right? ¿Cómo se dice, Swedish? Water. All right. Other languages in here. Water. Huh? Okay. Agua. But what about Russian? Anyone speak Russian in here? Arabic? Are any of those water? Were any of those water? They're all water, right? Agua, all water, right? But you don't say it like water. In lab, we're gonna have these little things called beakers. In English, it's called a beaker, but not in Spanish, not in Swedish, not in Afghan, any of that. So the problem with the alchemists is they didn't have a common language. So they couldn't tell anyone how to replicate what they've done because they couldn't tell them in their own language. Now you have to remember back in the 1600s, 1500s, towns like Paris were villages. London, village, not a huge metropolis. Frankfurt, village. And to go from one village to the other is by two ways. You walk or you're riding a donkey. So communication was very poor in those days compared to now as well. So those are the two challenges alchemists had. There's no clear way to replicate their information, nor willingness to share it. And secondly, their language was inconsistent because they spoke different languages, didn't. Okay, nowadays, all that's fixed. Period. I mean, no exceptions. When I was in graduate school, you have to publish. And when I published, man, it was the Journal of Oil Chemists. And man, it's called peer review. And that means all my peers had to review what I've done and whether it was reasonable or not. And then the editors of the magazine said yay or nay. They still didn't necessarily publish it. So peer review is very important in both medical, any kind of science, engineering, all that's called peer review. Alchemists didn't do any of that. Additionally, there were other civilizations, like I already mentioned, the Nubian, Middle East, Asian, all had their own science programs going, and they were way ahead of Western Europe, like way ahead. And so, you know, Western Europe tends to think that they're the focal point of everything. Or not. And nowadays, particularly. Okay, the first Western European physicist was Dalton. And now Dalton, he brought back Democritus' atom. He said Aristotle's concept wasn't valid. Or that's what he was saying anyway. It revolutionized physics and chemistry. It's very important. It's a landmark in science. It wasn't entirely correct, but it was still a landmark. This is what he proposed. Matter is composed of indivisible particles, atoms. Now, when he said indivisible, I notice I notated it there. They are divisible. They're called subatomic particles, and there's quite a few of them. There's about 50 of them. the three main ones everyone's familiar with are electrons, protons, and neutrons, but there are lots more. There's muons and all kinds of fancy, funny names. But anyway, it is divisible. Now, number two is kind of interesting. All atoms of a particular element are identical. So if you got a slab of gold, all the atoms in that slab of gold are gold. It's like, duh. But that was a big deal in those days. And number three is kind of the antithesis of that. Different elements have different atoms. So the atoms of the pencil and the atoms of the stapler aren't the same. Is that wildly profound? Now, this is important. Number four, atoms combine in a certain whole number ratio. What's the formula for water? H2O, not H 2.10. It's exactly 2 hydrogens, exactly 1 oxygen. Because we cannot split those atoms when we combine them into a compound. They have to be whole, hence whole number ratios. So, test question. How many sig figs is that? 2 and 1. How many sig figs is that? I hear 3, 1.
What number is?
H2O. The 2 and the 1.
It's 2.
Infinite. Hmm?
Conversion.
It isn't so much as a whole number, it's by definition. Because you can't have part of an atom. It's exactly a whole number. In which case it'd be infinite. Like by definition, sort of. Remember we said anything by definition has infinite sig figs. Okay, and number 5 says the chemical reactions atom are merely rearranged to form new compounds. They're not created, destroyed, or changed into atoms of any other elements. Well, that's not true. It's called nuclear chemistry. We do it all the time. So that's, and they didn't know about nuclear chemistry in those days. So it appeared like when you do a chemical reaction, I'm going to talk a lot about chemical reactions. Well, a chemical reaction is basically you take what you start with and you take it apart and then reassemble it. And what you reassemble is more stable than what you started with. Otherwise, it doesn't happen. And that's where Dalton was going with that. The problem is there's something called E is equal to mc squared. So we can interconvert the matter to energy and back and forth. So all of a sudden those starting materials can vaporize. It's called a bomb or a nuclear power plant, but it can be changed. So those are some of the weaknesses of his theory, but the main thing is it was revolutionary. It was a big deal. And is given a lot of credit. Okay, and this basically summarizes it. Okay. Now the problem is Dalton didn't talk about how the atom is organized. By now, a guy named Thomson said, we need a model to kind of talk about this. His model was called the plum pudding model, which is basically a glob and everything is kind of thrown in there. And there are 2 things thrown in. One is called corpuscles, renamed to be electrons. And the other thing were something that's the exact opposite charge from corpuscles, which are positive. So Thomson's responsible for plum pudding model and electrons. That's all you need to know about Thomson. And this is what he looked like. And he back-ended the discovery of the proton because something had to have an equal charge against the electron. Okay. All charges have a value. It's called coulombs. And the more coulombs, the bigger the charge. So Millikan determined the charge of the electron. And it's a very famous experiment. It's called the oil drop experiment. Basically, he took a drop of oil and suspended it in a vacuum. So it didn't go up or down. And he was able to figure out what the charge was based on that experiment. All you need to know, though, is Millikan charge of electron. Rutherford. Now, he tried to prove Thomson's plum pudding model was correct. So what he did is he shot a gold atom with a bullet, an atomic bullet called an alpha particle. An alpha particle is a very heavy nuclear radiation. It's composed of 2 protons and 2 neutrons, but it's big compared to all the others. He used that as the bullet. And he shot the gold foil, and something weird happened. Everything went through it. Now, with Thomson's model, what would go through it? Nothing. Solid. It bounced off just like a billiard ball. But with his experiment, everything went through it. Yeah, what the heck? So his idea was that there's maths there because occasionally, like 1% of the time, one would bounce off. Very small number, probably even less than 1%. Excuse me. So he came up with the idea of the nucleus. And he got a Nobel Prize for his nuclear chemistry work, not for his discovery of the nucleus, but very important guy. So Rutherford determined that everything is empty in that atom except for one thing. It's called the nucleus. And all the mass, 99.9999%, not 100%, is in that little bitty nucleus. And I'm saying little bitty. Now let's look at how little bitty that is. If you look at a stadium, a professional stadium, in the middle of that stadium is a marble. A little bigger than that, but basically a little marble. That's the ratio of the whole atom to the nucleus. And what's inside the nucleus? Protons and neutrons, right? And what's the charge of neutrons? 0. What's the charge of protons? +1. What happens to particles of like charge? Do they like each other? No. They horrendously hate each other. It's like my second marriage, you know. Oh, sorry. We took a horrendous amount of force to keep those protons from flying apart. And that's called nuclear force. So think about the whole stadium, that little bitty nucleus, and those protons jammed in there. Now, uranium, for example, has 92 protons, all jammed into that nucleus with a whole bunch of neutrons. Now, neutrons aren't charged, so the nuclear force doesn't come into play in keeping them together, but those protons are the problem. So now we have a new model, and it's a funky one. Basically, I'm standing on nothing. That's what Rutherford said. So do you think that was controversial back in the 1800s? Do you think that was very controversial? So he had to have a lot of data to back up what he was saying. Lots of experiments that were very reproducible to back up what he's saying. Now, he didn't say anything about organization. He said that, so there's electrons flying around, and then there's this tiny mass or tiny spot of mass for the whole atom, composed of protons. and neutrons. Now, he didn't know about neutrons at the time, but inside the nucleus, except for hydrogen, there are protons and neutrons. So Rutherford nucleus. So this is another example of what it looked like. So what he did is he shot that gold atom and everything went through except a couple times it bounced. So with Thomson's model, everything should have bounced. Okay, Chadwick. He discovered the non-charged particle the size of a proton. It's called the neutron. So Chadwick, neutron. Aston discovered that if we look at something called isotopes, the chemist, do you have a question?
I have a question about how they bounce off the nucleus. I know the chances are astronomically unlikely, but what would happen if they had hit an electron instead?
Well, an alpha particle is huge. We're talking about an 18-wheeler versus a bicycle. I mean, it's even grosser than that. But so what would happen to the bicyclist? Yeah, so the electron wouldn't have any effect. However, the charge on the electron is equal to the charge on a proton, but opposite. So the coulombs on each one are equal, but opposite. But the size is horrendously different. 1/30,000th different. That's how big the proton is compared to the electron, or the neutron compared to the electron.
So wondering if the alpha particle hit the electron directly, would the electron become attached to the alpha particle? Would it be flung away from its original atom? Would it become a different element?
No, because protons determine the element, not electrons. I'm going to talk a lot about that actually, because electrons come and go. Protons don't. If the protons go or increase, it's a different element. So it wouldn't be gold anymore. Something else. Interesting question. Okay, Ashton said, if we look at certain elements, they kind of chemically act the same, but they weigh, their mass is different. I'm going to start calling those isotopes. Now, an isotope differs in the number of neutrons. Protons are equal. So we're going to have so the number of protons are the same, hence the chemistry is the same, but the number of neutrons are not the same. So we can have carbon-12 and carbon-14, both carbon, chemistry of carbon is the same for both of them. The mass is different because they have different numbers of neutrons. Ashton came up with that. Now, this guy had an organized sock drawer. He believed that all the socks have to be in a certain order. And unlike my drawer, my sock drawers are not organized. They're organized by color alone. I wear white socks or black socks. That's it. So I have a drawer for white socks, a drawer for black socks. I can reach in and grab two socks, and I know they're going to match. So that's the opposite of OCD. My second wife was very, very, very OCD. So she had her bureau, and I had my bureau. And mostly we got along, but it was an issue. Okay, so Bohr has organized sock drawer. So he says these electrons going here, hither, nether, whatever, that's not the way he envisioned it. So he wanted organization of the electrons. Organization of electrons. And he came up with this idea of, who's seen the movie Men in Black? Anyone? Okay, what was on Orion's belt? Who's Orion, first of all? Orion was the cat. So what was on the cat's collar? It's an old movie. The universe. And a little glob on the cat's collar. So Bohr hadn't seen the movie, but he envisioned the same sort of thing inside the atom. He envisioned this planetary-like solar system inside the atom. He said, how poetic is that? That's pretty cool. So he said, we have the nucleus, sun, planets going around the sun, electrons going around the nucleus in orbitals, just like planets. So Bohr came up with this concept of orbitals. Now, orbitals closer to the nucleus are smaller. Hence, they can't have as many electrons in them as orbitals on the outside, just because they're bigger diameter, more space. So he defined the number of electrons per orbital, like the innermost orbital can only hold 2 electrons. Now, they're only allowed to be on an orbital pathway, not anyplace else. Only, no exceptions, only on one of the orbitals. What happens is the orbitals vary in stability. The closer the orbital is to the nucleus, the more stable it is, because electrons like positive protons. So the closer they are to the nucleus, the more stable that orbital is. So when you're throwing electrons in this atom, the inner orbital is going to fill before the outer orbitals. Now, there's some exceptions to that I'm going to talk about in a minute here. So these are the numbers, 2, 8, 8, 18, etc. The main thing with Bohr, you have to remember about 3 things. Orbitals, as opposed to unorganized electron movement. Secondly, each orbital is predetermined to have a certain number of electrons maximum in it. How many electrons can fit on that orbital? And lastly, electrons can go from a stable orbit to an unstable orbit by pushing energy into that electron. Fluorescent lights work on this principle. We have a transformer inside the fixture. It's called a ballast. That ballast supplies high energy to the gas inside the tube. That energy then takes electrons and moves them up to a higher unstable orbital. Now, things in nature don't like, that's why it requires energy. Nature goes from unstable to stable. And we're going to find that's true with chemical reactions. Unstable to stable. If in doubt, it's because it's more stable. The rest of the semester, if in doubt, it's because it's more stable. Okay, so what happens when something goes from unstable to stable? It gives off the same amount of energy that it took to get there. So if it took 5 electron volts to get from one orbital to the other, when it becomes more stable, coming back down to the more stable orbital, it gives off that energy. And the energy is invisible for fluorescent lights. That's why we see it. But there's a lot of other energy being given off in the ultraviolet and infrared as well. Now, when you touch a fluorescent tube that's been on for a couple hours, it's not hot, but it's definitely warm. And that energy is in the infrared. So that's another important part of Bohr. So what he did, we have orbitals, and we have a nice ground state electron That means it's the most stable state it can be in that particular orbital. And we zap it with some energy. It's going to go up to a more unstable place. And that's called the excited state. Now, it takes an X amount of energy to put it there. And when it comes down, it's going to give off that amount of energy. So if we have 5 electron volts to get it there, when it comes down, it's going to give off 5 electron volts. Electron volts measure of energy. Okay, so Bohr, 3 things: orbitals, fixed number of electrons per orbital, and the electrons can go from one orbital to the next, either requiring energy or giving off energy. Bohr got the Nobel Prize for this. Big deal. He did a whole bunch of other things as well. He's a very famous physicist, but this was a big deal. Okay. Yeah.
The slide above, you were talking about, I forgot, something being, and when you touch it, it's warm, and then. So is that like the same thing as a light bulb, like when you touch a light bulb, is that this, it's been on for the, like. so
No,
long
it's just that
it's hot?
the energy being given off is in the infrared. Infrared energy is, you feel it by heat. So not all the light, or let me back up. Not all the energy is being used to produce light, visible light. It's being used other energies.
Oh, okay.
Infrared, heat, and ultraviolet that we can't see. Bees can see ultraviolet, but we can't. And that's what gives us, reactions with our melatonin in our skin. That makes sense? So energy is a big, long spectrum. It's huge spectrum. And we only see the visible. Okay. Now the quantum model, Bohr's model, had issues. One of them is to require an electron, and Rutherford says the same thing. To require an electron to be in an orbital, it requires energy. If you don't supply it with energy, it's going to do one or two things. It's going to spin into the nucleus, or it's going to spin out in space. So that was one of the problems with Bohr's model. So we invented, now it's been about 120 years now, the quantum model. The quantum model also talks about orbitals, but in a very different way. It's a statistical model. It's not saying how the electrons are getting around. It says, where do I find them? Let me give you an example, concrete example. Let's go over to Rayleigh's. On the side of Rayleigh's is a door, and a whole bunch of cigarette butts are on the ground. How'd they get there? Okay, smokers need a place to smoke, not inside Rayleigh's. They go outside to this one place, designated place. And you know how smokers are, they flick their butts. Like my daughter smokes, and always on her case, don't flick your butts. When I was in the Air Force, we had a butt can, and we had to field strip our cigarettes into the butt can. None of this flicking stuff. However, we don't know if it's an employee cigarette butts or a customer cigarette butts. Do we know where to find them? Yes. We go to the one door on the side of the building where all smokers go. That's the quantum mechanical model. We don't know how the electrons get in these areas, but we know where to find them statistically. And it's a very nice concrete example of a quantum mechanical model. So quantum mechanics is not a planetary one at all. It's very different than Bohr's concept of the planetary system. And we have probabilities, statistical probabilities of where to find them. And quantum mechanical models have orbitals, but they're not planetary orbitals. They're just areas of probability where we can find electrons. And it varies. So going back to the Rayleigh's example, if we go out in the hallway here, are we going to find a cigarette butt? Probably not. Like high odds that we won't. Yet at the Rayleigh's place, there's a high probability we're going to find a cigarette butt. So no orbitals over by Rayleigh's. And we have no way to know how those butts got there. We have no way to know that statistically, now the probability is not zero. Probability is very low, not zero. Okay, so that's where we are. Quantum mechanics is a god-awful class. It was the hardest class I've ever taken in my entire life. It was a whole quarter long, just quantum mechanics. And that's why you take calculus if you're a chemistry major. And all you do is calculus in there. You do differential equations and calculus. And it's that was a math major. I thought it was a hard class.
Oh, dear Lord.
Yep, that's what I said. Okay, from quantum mechanics, it tells us each electron has an identity. Now, I have to talk about periodic table before we get into the quantum. Okay. Okay, so let's look at the periodic table. I'm going to come back to the quantum mechanical model, and we have to talk about how the periodic table is organized. Okay, there are basic levels of organization in a quantum mechanical model. The biggest one is called a shell, and then it keeps getting finer and finer after that. So it goes shell, subshell, orbital within the subshell, and then the magnetic spin of the electron. Now, electrons are little magnets, and they have magnetic spin. That's why something is magnetic and something's not. It has to do with the electrons, how they're arranged in the atom. Basically, if the electrons are paired up, all of them, then you have no magnetism. If it's an odd number where some are unpaired, then the thing is magnetic. So you've got 4 levels, okay? Shell, subshell, number of orbitals in the subshell, and the spin plus or minus. Okay, so where organizationally on the periodic table are shells? Okay, so if we have shell 1, it's the first row in the periodic table. So in shell 1, we have hydrogen and helium. Shell 1. Shell 2, we've got lithium. Let's see. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Shell 2. Now, we have subshells, which are subunits of a shell. So those, you subdivide the row into subshells. So if we look at shell number 1, how many electrons on the Bohr orbitals was the innermost one, you remember? 2. Notice that shell 1 has 2 electrons, possibly. And then as we go into subshells, it goes more and more subshells the further we get down the list. Okay, so let's look at shell 2. Shell 2 is made up of 8 elements. Shell 2 is made up of 2 subshells. S subshell and P subshell. Okay, and this is the S's, and these are the P's. Again, those are just in certain statistical areas around the atom, around the nucleus. Yeah,
So. I don't know, like, jumping, but the numbers under the, that was like that.
okay, underneath the symbol, okay, there's a number above it and below it.
I'm at.
Okay, that's a decimal, you're talking about the decimal number, right? That's called molar mass. I'm gonna get into that in immense detail. It's the mass of the atom if you add up Avogadro's number, 6.02 times 10 to the 23rd.
Related mass thing.
Yeah, that's why gold weighs more than iron.
Above, just because we're.
Just real quickly, the number above is the number of protons.
Got it.
So you look at carbon,
The person who created it knew that there would be blank spots for other atoms that have not been discovered yet.
sorry,
I knew that there was a reason, I forgot what it was.
you remember who that person was?
No, I only know that the person who did the cell model was someone named Mendel.
Mendeleev, the Russian guy.
Yeah, sounds like Mendel, so that's why I remembered it like
Yeah, yeah. Actually, Mendeleev was the second guy. There's a guy,
the square.
right, that's why the periodic table is square shaped. There was a guy before him who was a geologist that came up with the idea, but he didn't publish. Mendeleev published, and that's why. Well, it wasn't because of that, but it was because publishing. And
Yeah. And I'll
yes. They get a lot more credit now than they did before.
politics of today are pushed backwards.
Okay, so S subshell, P subshell. Okay, we've got two more subshells. The electrons that are in the middle here are called D subshell. Those down here are called F subshell. And those are just different areas statistically. Now we're gonna, in this class, we're not gonna talk much about the F subshell. We're gonna talk a lot about the SP and D subshells though. Because basically quantum mechanics allows us to identify by electronic configuration every electron in the atom. And this identification has to do with these four parameters. And then there's a bunch of stuff, for example, if based on electronic configuration, you can determine if an ion is going to form or not. Or if the atom is stable. You look at its electronic configuration, and it'll tell us that. And again, we're going to get into that big time. Okay, so let's go and go on. This was a guy that was very famous, and he didn't live very far from us. This guy was out of Berkeley. He discovered 8 new elements. His name was Seaborg. And there's even an element called seaborgium named after him. Now, the reason why I brought him up is when I was in graduate school, we were required to have a seminar once a month. And he would come to our seminars all the time. Because I went to Davis, so Berkeley's not that far away. Because we had a really varied subject of all the seminars. So he really enjoyed going to it. Really a tall guy. He was in his 80s when I met him. I'm sure he didn't remember me from every other graduate student. Huh? He's not living any, yeah, because of the death date. Yeah, or theirs was right here. It's not the same thing, but okay, anyway, cool guy. I just want to give him credit for that. Okay, and then Oh, is this a nice segue?
Yeah, I should have waited, but we're.
Oh, that's okay. All right, so this is what Mendeleev early periodic table looked like. Yeah. Pretty bad. Well, they didn't have,
Pages like diary, like Indiana Jones stuff.
that's right. And they're, like you were saying, there are empty spots there. He was able to predict that they were going to discover elements there. Now, the modern periodic table, this is a bigger picture of it. The modern periodic table looks like this. Notice it's really, really wide. So these are the S's. These are the P's. These are the D's. And these are the F's. Now,
What is that?
the only one that makes sense is S for sphere. Because,
Porsche.
yeah,
Well, no.
that's the only one that makes sense to me is sphere. The others are weird and I don't get the connection. Why they're called that? Huh?
Are we talking about shapes?
Yeah.
I don't know, if it looks like a face, and then maybe it looks like a diamond, and then.
No, they don't look like that at all.
Oh, it just starts with those letters.
Okay, so what happened is they for simplicity reason, they pulled out the F's and put them on the bottom here. So this is what our periodic table looks like now. It was just for convenience.
Natural history of the periodic table.
Well, part of it, yeah. Okay. And this is what Mendeleev looked like. For all of you who speak Russian, sorry, I don't pronounce it very well, but. Now, the thing I want to really hit home on this presentation today has to do with something called induction versus deduction. Now, you've heard these terms, probably deduction more than induction. Deduction is you're talking about something general to the specific. For example, math. Addition. We can talk generally about what is addition. And then we can go 2 + 2 is 4. That's specific. Science is not deduction, though. Science is induction. So what we've done is we've gone through the models of the periodic of the atomic model. We start off, very vague data, and we gradually added more and more data. When we add more data, we have to refine the model. And that's what induction is. So we take specific stuff, specific data, and form a general model from it. And then we can predict from that. And that's where the scientific method comes in. So my point in this is science is not static. It's constantly changing. Within the last year, something very major happened.
Thing?
Hmm?
The Direwolf Grey Wolf thing? That was major in the scientific community. They thought that they brought back from extinction direwolf, but it was really gray wolf with a lot of modifications.
I'm talking about something different. Who's heard of Voyager 2?
Oh,
Anyone?
well then I wouldn't know.
Bro. Isn't that the bro that's out past your arms? Whatever.
Yeah.
Now, but
It was launched in 1977 and it's 2 billion miles out. However, something mysterious happened in the last year. Its power supply got turned on. They thought the power supply was depleted.
This is a cracker.
It's a satellite. No, it didn't crash. And
Oh yeah,
Oh,
abandoned,
a
right?
mess. What?
Abandoned, right?
No, it just sent out. Yeah, wasn't abandoned. And but they thought it was the power had gone out. And apparently something turned it back on. and something that turned it back on sent back a message.
Well,
Mhm. A message. It said, "Stay on Earth."
I'm guessing that was a hacker who's sending a very not so funny joke.
I would love to be in there.
Yeah, same with me.
It's going to be funny because they're messing around with their equipment and it's used for serious purposes.
Honestly, the scientists who work on it are probably along. So.
Well, no, I mean like the scientists who continue to work on the satellites. Because there aren't just gonna quit satellite scientists, you know, there gotta be some to continue to this day.
And so we have science induction, math deduction. Religion is also deduction. You start with the sacred scriptures and you go from there. So that's another example of deduction. But science is induction. Induction. And that means what's true today won't necessarily be true tomorrow because the data doesn't support the current model. That's why we went from Bohr to quantum mechanics. The data did not support Bohr's model at the time. Okay. All right. So the main things I want you to know about the scientists that worked on the model ends at a quantum model. You don't have to worry about Seaborg and some of those other things. So we start off with Democritus and Aristotle. Then we went to Thomson, one pudding model and electrons. Then we went to Millikan, which determined the charge of the electron. Then we went to Rutherford, who discovered the nucleus. Now, Rutherford also talked about Bohr's concept of the planetary model. But Rutherford is known for his gold foil experiment. But he didn't get the Nobel Prize for that. He got the Nobel Prize for his other work. These guys did a whole bunch of stuff. And then Chadwick came up with the concept of the neutron. And then Ashton came up with the idea of isotopes. And then there's Bohr. 3 parts for Bohr. He defined orbitals, number of electrons per orbital, and then the concept of electrons can leave an orbital, go to another one, and come back. And then there were some issues with that, and they came up with quantum law. And that's where we are now. It's still a valid model. Yeah.
Walter, would you mind going back to the last slide? I didn't get the science deduction portion of it. No, the very last slide I called. Where you talked about science induction and science deduction.
This one here?
Okay.
Okay, so that's it for today. And so tomorrow we're having our tests. Wednesday, I'm going to get into much more specifics on the periodic table in terms of electrons, neutrons, protons, how many, what's going on with that. Yeah.
Will you be posting? Where, for lecture videos, where would I go?
Modules.
There.
Or you could just look up his first and last name on YouTube and then go to his account.
Additional things in modules besides videos. It's easiest if you start with modules. Like she said, it's true though. I have a channel, YouTube channel. I've got about 350, 400 videos on it from all of it. So what I do,
Yeah, on the front page of it, it'll have upload, so just figure out how many days ago it was, and then, 24 hours a day. Go from there.
what I do
Wonderful.